Good morning. My name is Bob Armstrong. I'm director of the MIT Energy Initiative, and it's a pleasure to have you here with us this morning to roll out the Future of Energy Storage study that MIT, MITI have been working on for the past several years. I'd like to start by just giving thanks to the AAAS, the American Association for the Advancement of Science, for use of these very nice facilities so that we can do this presentation and hopefully have some interesting Q&A at the end of the presentation. Let me start by framing the study and what motivated us. First and foremost, avoiding the worst impacts of climate change mean that we need to drastically reduce greenhouse gas emissions by mid-century. I think we are all aware of that. A key part of doing that is a deep decarbonization of the electricity sector. And along with that deep decarbonization of the electricity sector, electrifying as many other parts of the economy as we can do. And that means that we need to decarbonize the electricity system at reasonable cost. A deeply decarbonized electricity system, of course, is going to rely heavily on solar and wind, intermittent renewable energy sources. And that means that energy storage is going to be an essential part of getting us to these deeply decarbonized systems in an economic and reliable way. So this study is aimed to address some of the key questions in enabling that. Specifically, what kinds of technologies, what kinds of policies would help make this feasible as we go forward? How do we do this differently from region to region around the US and around the world? The mix of resources we have to deploy is different, and so will be the electricity systems of the future as we move to a deeply decarbonized system. In this study, we studied a variety of different technologies. We dug deeply into these technologies to understand their characteristics and how they might play in a future decarbonized electricity system. We looked at four major categories of technology: electrochemical technologies, mechanical technologies, thermal technologies, and chemical technologies. Interestingly, we find that those technologies play in a wide variety of the storage need space, from fairly short duration storage on the lower right of the graph I show here. Lithium-ion batteries fill that space very nicely today, up to, on the upper left-hand corner of this graph, long duration storage, which is increasingly important as we get further and further along deployment of these intermittent renewable resources. So that's the space we looked at in the study. You'll hear more about that as we go forward through discussion of the different elements of the study. So what are our messages here? We have three main messages that we want to address in three different segments of this presentation. First, on the technology side, we think it's important for federal R&D policy to focus on long-duration storage technologies to support affordable, reliable future electricity systems. Secondly, we find that storage can make regionally tailored net zero electricity systems affordable, and that's key. And then lastly, market designs and regulatory policies need to be reformed in order to enable equitable and efficient decarbonization. So let's start with the first of the three messages here. And to do that, I'm going to turn over the podium to Yetning Chang. Professor Chang is a professor of material science and engineering at MIT, and he headed up the technology session. Hold on one second. So I'd also like to introduce the other panelists up here who you'll hear from in turn. Next down the table here is Elsa Olivetti. She's a professor also of material science and engineering. Next is Darek Malapragada. He's a principal research scientist at MIT in the MIT Energy Initiative. Next is Rob Stoner. He's the Deputy Director of MITI for Science and Technology, also an expert in developing countries, head of the Tata Center at MIT. Next is Professor Dick Schmalensee from the Sloan School of Management, former Dean of the Sloan School. And then finally on the far left, or your far right, is Professor Paul Joskow from the Economics Department. So these are all experts in different aspects of this area, and really looking forward to hear their insights. Yeah?
Thank you, Bob. I'd like to say a little more about this first takeaway message, which is the topic of long-duration storage. So one thing to recognize is that, technically speaking, any storage system can be discharged over a long duration. The key question is, can it do so affordably? Right? And in terms of the cost targets, we can think of the fact that in order to compete with today's natural gas electricity generation, for example, if it's a multi-day gap that we have to cover, let's say 4 days, 100 hours, the cost of the storage has to be about $20 per kilowatt hour or less. And so in carrying out this part of the study, we looked at emerging technologies that might have the capability to do that, to do multi-day storage affordably. Right? There are four main categories here that I'll speak to in long-duration storage technologies. And let me begin with mechanical energy storage, the lower right here. And one version of this, pumped hydroelectric storage, is in fact the largest deployed storage today for the grid and has been around since the early 1920s. Right? Now, all mechanical storage systems inherently have lower energy density than, for example, batteries. And so they imply a large footprint. And it turns out that while today pumped hydroelectric storage is scaling rapidly in other parts of the world, in China, in other parts of Asia, as you see in this plot, in the US, we're constrained by geology, right, by permitting, and by the very long cycle for construction. And so we don't see mechanical energy storage as playing a key role in long-duration storage going forward. Other technologies like compressed air, which for low cost require underground reservoirs as well, are limited by similar considerations. Right? In the upper left here, redox flow batteries. This is a technology in which there is a power stack which is separate from energy storing tanks. And so inherently it decouples power from energy. And this can be designed for long duration storage. Today, most of the redox flow batteries we know have been developed for relatively short durations, and the leading chemistry here is vanadium-based. And as you'll hear later from my colleague Elsa, there's, at least in the near term, supply and cost constraints to using vanadium. While this architecture looks attractive, and we believe it is attractive for long-duration storage, we're really still awaiting a breakthrough in chemistry, that low-cost chemistry that can really make this architecture and this technology sing. Right? All right, let me now turn to thermal storage. In the study, we identify an option, a retrofit option, which has not seen a great deal of attention, which is related to the fact that the key challenge in thermal storage is turning that heat back to electricity. Okay? And so the cost of converting heat to electricity is the barrier. And in fact, existing fossil fuel plants have that capability already, from the turbines downstream. And so one low-cost and potentially rapidly scalable form of long-duration storage would be to retrofit those plants so that on the front end, we use renewable energy, primarily electricity, in order to heat a thermal storage medium that then drives the power generation. And of course, these are already grid connected. Okay. So the last long duration storage option I'd like to talk about are metal air batteries, a particular chemistry, which today, if you use for metal air batteries low-cost metals like zinc or iron, these have the lowest cost entitlement of any rechargeable battery that we know of. Okay. They have some flaws, such as a relatively high power cost and low round-trip efficiency, but the long-duration storage application is tolerant of these limitations. Okay. So they're, in many ways, ideally suited for long-duration storage. And from a supply chain perspective, these are using metals that are already produced in huge volumes for other applications. And so just as one example, in the iron-air battery case, to scale to a installed storage of, let's say, 100 terawatt hours or so by mid-century, which is what some studies have indicated will be necessary, that would require only an increase, a compound annual growth rate in the production of iron of 1% or so. So we see that as an attractive option. In the area of chemical energy storage, the leading candidate is hydrogen, of course. Right? And there are many initiatives ongoing related to hydrogen, which we think we all support. For long-duration storage, the key barrier is the fact that using hydrogen to produce power, again, that stored hydrogen to electricity cost, is today more costly than competing fossil fuel power plants such as natural gas power plants. Right? So over time, we believe that the cost of generation, the cost of storage will come down, will be favorable, right? But that cost of electricity generation will be the key barrier. And the other reason that we don't think hydrogen is likely to become the technology of choice for long-duration storage is that it competes with a lot of more valuable uses for hydrogen. And so there are other hard-to-decarbonize sectors of the economy, such as long-distance transportation fuels for which hydrogen can be used. And so those may be a more attractive use of the hydrogen that we produce. Okay, so then, what about lithium-ion? And I've not said anything about lithium-ion up to this point. And it's pretty clear that for EV applications, there's nothing on the horizon that is likely to displace lithium-ion anytime soon. And so the scale-up of lithium-ion production will, in the near term, go primarily towards electric vehicles. Right? So the availability of lithium-ion for grid storage will depend in part on that growth. For short durations, lithium-ion, however, short-duration grid storage, lithium-ion will remain a preferred technology. And today, that's 4 hours or less. With the continued cost down of lithium-ion, that could grow to as long as, say, 12 hours. Right? So in the middle chart here, what I show is this cost decline over 3 decades. I think we're all familiar with how rapidly and how far the cost of lithium-ion batteries have decreased. Right? On the right, this is the projected increase in production of lithium-ion batteries over the current decade, 2020 to 2030. It's likely to increase by a factor of 5 times. Right? At the end of the decade, it will be at about 2.5 terawatt hours per year. Right? Now, that sounds like a lot, but in light of a target like 100 terawatt hours by mid-century, there needs to be a continued scaling of this magnitude, greater than about 20% CAGR, year upon year for the next 28 years. Right? So that's what using lithium-ion for grid storage would involve. And there also are supply chain challenges, which I'm going to now hand over to my colleague Elsa Olivetti to speak to. Right.
Thank you very much, Jet. So Jet has outlined some of the technologies that we covered in the study, as well as some of the challenges and opportunities in those technologies. And in particular, what we focused on as an aspect of this was the ability for materials, the sort of element minerals-based supply chains, to respond to the sorts of trajectories that Jet outlined and that are also outlined on this slide. And in particular, the picture in the middle points to why we care about materials availability or minerals availability when it comes to the challenge of scaling rapidly. As these costs decline, over time, we then confront this floor associated with the price of minerals, the price of materials. And so any volatility associated with those materials will then contribute to overall challenges when it comes to rapid scaling. And rapid scaling was essentially our punchline in looking at the relevant minerals for the sorts of energy technologies that Jet outlined, energy storage technologies that Jet outlined. So really, it's not about a limited availability of these materials. There's not a limit in resources per se. The economically viable reserves has been increasing despite increasing demand. It's about our ability to scale that infrastructure as rapidly as it needs to in a stable way to address the risk associated by the adoption of those technologies. So the reason we care about materials availability is not about running out, it's about its impact on price and about the volatility or the perceived volatility of that price in scaling as rapidly as we need to. And so you see that point reflected in the first bullet here. The set of elements that we focused on in the study were those that were driving the lithium-ion battery technologies that Jet outlined, lithium, cobalt, and nickel, and then also looked into vanadium as well, as Jet outlined as the leading candidate for materials in redox flow battery chemistries. And so not resource limited, but really production limited. And this is exemplified by this table in green here, where for each of the elements that I outlined, we've defined the historic range over the past several decades in the compound annual growth rate of the scaling of those materials compared to what that growth rate would need to be for that 100 terawatt hour benchmark that Jet spoke to through 2050. And you'll see in sort of coming out in red there the challenges where we see lithium is on the upper end of the historic CAGR versus cobalt, which we know also has other associated challenges in terms of the concentration in both the extraction of the material in the Democratic Republic of Congo, but also the refining of that in China, and I'll come to that in a minute. Nickel as well, as we transition in the lithium-ion battery space away from cobalt into nickel-based chemistries, we start to see a particular challenge in scaling nickel that has been historically relatively stable in the 0 to 5% compound annual growth rate because of its links to steel. And so the rapid growth that would be associated with a significant shift from cobalt into nickel offers challenges there. There's also a subtlety when it comes to nickel in that the majority of nickel as currently extracted is not at battery grade, and so there'd also need to be significant investment in the infrastructure associated with the extraction and refining process in order to meet this demand. There's a lot of uncertainty associated with our ability to meet that demand. As Jet said, that there's this sort of long time for new mining projects to start up, et cetera. But that's also the fact that there's uncertainty in the technologies that will be deployed. And that's demonstrated just illustratively in the plot on the right that is showing the compound annual growth rate as a function of what the integrated deployment would be this is in the lithium space for lithium-ion battery deployment. And those several colored strips there have to do with which chemistries are we exactly pursuing, what do we mean by a nickel manganese cobalt battery, and at what level of the market is lithium being used in batteries versus the other applications. So that sort of lays out the dynamic space that's at play here. And then there's a brief line there at the bottom around vanadium, which in order to have any significant deployment would have to really exceed the historic compound annual growth rate by quite a bit. And there's a lot of challenges associated with vanadium in terms of the dispersed set of secondary sources that production could come in the form of. It's very coupled to the steel market, which offers other challenges there that we can come to. So one point that isn't covered in this slide that we'd like to particularly draw our attention to has to do with the significant shift in supply chains that we see already happening, but that would need to happen much more significantly in the myriad scaling that would be required in terms of extraction of new minerals to support energy storage technologies. So here we're looking at geographic share, the top 3 producing countries, comparing fossil fuel extraction and processing for oil and natural gas and oil refining and LNG export on the top 2 bars there compared to the geographic distribution associated with the minerals that are necessary for energy storage technologies. And you see just even not noticing the countries, just the shift in color from the top to the bottom set points us to a much more diverse set of supply chains, and particularly, as we know well, in the processing side, a very heavy reliance on China when we start to think about extraction of the minerals relevant for energy storage technologies. So just a highlighting there in terms of the geographies at play here. And so just to summarize this section around this first key message before we transition to the next message, as Yet spoke to, lithium-ion batteries have a set of characteristics, both in terms of energy density and power density, that mean that they're very relevant and appropriate in the electric vehicle market. And so their use in the grid storage-based technologies is most relevant for short-term duration and seen as in the grid for longer duration as not necessarily viable, particularly because of a cost concern. And so our takeaways from there have to do with supporting the development of these new technologies or newer technologies or application in the grid of these technologies beyond lithium ion to demonstrate alternative storage technologies that really rely on earth abundant minerals, yet focused on iron and zinc in particular. And then there are these opportunities that we didn't speak to directly in this message around thermal storage retrofits in providing electricity storage capacity as a near-term opportunity, and then hydrogen as playing a role, but really playing a role as it is also playing a role in the overall economy. And so in both of these cases, in lithium-ion case and in hydrogen's case, the grid, use of energy storage in the grid, is competing with these other forms of requirements there. So that's the key conclusions from the technology message that we spoke to in the report. And then to take us to message 2, I turn things over to Dark.
Thank you, Elsa. So in the next few minutes, I'll focus a little bit on telling you about our key findings regarding message 2, which is centered around exploring the role that storage would play as part of a regionally tailored power system, and as we look at decarbonized scenarios for these grids. So to sort of understand the drivers for storage adoption in power systems under decarbonized scenarios, we looked at 3 US regional grids as a representation of industrialized economies that have high service reliability and a significant share of natural gas generation, and also an emphasis towards electrification of many other end uses as part of an economy-wide decarbonization effort. So the 3 regions we looked at in the US Northeast, Southeast, and Texas, we think are interesting because they're starting at very different points with respect to their emissions intensity of their grids. But these regions are also endowed with different resource quality in terms of renewable resource availability, hydro availability, and as we look at electricity being an increasingly central part of economy-wide decarbonization efforts, the share of electricity demand growth that we would see in different end-use sectors is going to impact the electricity consumption pattern across these 3 regions in a very different manner. So in the Northeast, for example, one could see a shift from a summer peaking electricity system to a winter peaking electricity system. So based on these kind of assumptions and insights, our modeling focused on economically efficient power systems analysis under a range of technology and policy assumptions. And I'd like to just highlight a few of the main assumptions we make here before we talk about some of the results. So we focused on CO2 emission intensity limits ranging from 50 grams of CO2 per kilowatt hour all the way down to 5 grams of CO2 per kilowatt hour. And just for reference, the 5 grams of CO2 per kilowatt hour, if applied sort of at the US level, would amount to about 97 to 99% decarbonization compared to 2005 levels. We're also accounting for a substantial increase in electricity demand that is projected as part of a highly electrified economy. And we're also presuming continued cost reductions for solar, wind, and lithium-ion battery storage as we look out to 2050. That is consistent with the technology team's assessments that are part of the study, but also consistent with other sources such as the National Renewable Energy Laboratory's annual technology baseline projections. We are also, because we're looking at 2050, we presume that much of the existing thermal fleet has turned over, but we continue to have availability of the zero carbon resources in these regions, namely nuclear in the southeast and hydropower in the northeast. And finally, because we're looking at deep decarbonization as part of a net zero emissions power system, we continue to sort of explore the role for sparing use of natural gas in combination with carbon capture and sequestration as part of the power system set of potential resources that could be deployed. So our first set of scenarios, we looked at the availability of only renewables and lithium-ion energy storage as the sole energy storage technology that can be expanded along with natural gas generation with and without carbon capture. And so the chart on the left is basically showing you the generation mix as we go from a no limits policy scenario on emissions to a 5 grams of CO2 per kilowatt hour emissions intensity constraint across the 3 regions. And then the chart on the right sort of is presenting to you a system average cost of electricity change across these regions as we go from the no emissions limit scenario to the 5 grams of CO2 per kilowatt hour scenario. So there's a number of interesting insights that one can see here. So as we increase the tightness of the CO2 emissions constraint, we see increasing adoption of renewables, as one would expect, which are the most cost-effective way to decarbonize our electricity systems in terms of a generation source as we have it today. We also see large adoption of lithium-ion energy storage, both in terms of power and energy capacity, and we see a declining role for natural gas generation and a shift in the 5 gram per CO2 per kilowatt hour case to use natural gas with carbon capture across these systems. I want to reemphasize that these results are presuming, again, favorable cost reductions for lithium-ion battery storage, as well as renewables projected out to 2050. Another interesting insight that can be seen from this chart is that we're basically seeing very different outcomes in the no emissions limit scenario for the 3 regions, where the Texas grid decarbonizes much more rapidly and much more significantly compared to the Northeast system, which is sort of illustrative of the regionally diverse challenges that exist for getting to deep decarbonization for these power systems. Overall, as we sort of look at the near complete decarbonization of these power systems, we find that we are able to drive down emissions out of the power system pretty significantly without incurring a significant cost penalty or sacrificing reliability at the hourly resolution of the analysis that we carried out here. One of the other interesting insights from this analysis is that as we look at these economically efficient power systems, energy storage can substitute and complement all other types of resources on the grid. These include generation, transmission, as well as demand-side management resources. So as we think about realizing this economically efficient decarbonized power systems, one really has to be thinking about analytical tools that can monetize the various services that energy storage provides in conjunction with the other resources on the grid, both from an operational perspective and from a planning perspective. And so what we are recommending that more effort is paid towards the development of these analytical tools in conjunction with ISOs and RTOs to be able to prepare us to be able to operate these kind of highly decarbonized power systems. Transmission expansion, where allowed in all of our modeling, stood out as something that plays an important role in these in achieving these deep decarbonization scenarios in a cost-effective manner by basically connecting renewable-rich regions that are often far away from major load centers. We find that transmission also competes with storage, and so in locations where you have transmission, practical constraints on transmission expansion, you could see some increased storage adoption in those scenarios. However, given the well-documented challenges and the central role that we see for transmission expansion to achieve these decarbonized scenarios, we do recommend sort of the need for making changes on the regulatory structure to reduce the barriers for transmission expansion. So another piece of our modeling analysis focused heavily on trying to explore the impact of the availability of the emerging long-duration energy storage technologies that were talked about in the earlier part of this presentation, and their impact on these deeply decarbonized power systems. So as was discussed earlier, many of these nearly all of these long-duration energy storage technologies have lower energy capital costs as compared to lithium-ion battery storage. And in our modeling, what we find is that they help to improve asset utilization by reducing curtailment of renewables. To some extent, they also support reducing wholesale electricity price volatility, which you'll hear about in our third message. And they also support grid decarbonization by overall reducing the costs. So the chart on the bottom shows you the system average cost of electricity for a number of technology scenarios that involve long-duration storage as compared to the base case where we did not include these long-duration storage technologies for the 5 grams of CO2 per kilowatt hour case, as well as the fully decarbonized power system case where we're basically primarily relying on renewable resources to achieve a zero carbon power system. So what we see here is across the two scenarios is that the availability of long duration energy storage reduces costs, but these cost impacts are most dramatic as we go to the 0 gram per CO2 per kilowatt hour scenario where natural gas generation is no longer an option. Given the substantial role that they can play in some of these scenarios, we are recommending that we have increased public and private R&D to improve the cost and performance attributes of these resources to be able to support grid decarbonization. My last point here would be on focusing a little bit about highlighting the role for hydrogen in grid decarbonization efforts. So as was mentioned previously, hydrogen is differentiated from many of these other longer duration energy storage technologies due to its potential role in economy-wide decarbonization in sectors where direct electrification may be impractical. These could include industrial demand sources, but also the heavy-duty transportation sector. So in our analysis, we looked at long duration energy storage representation of hydrogen where you have an electrolyzer that's converting electricity to hydrogen that you're storing and subsequently converting that hydrogen back to power at times when the grid needs it. However, these same assets could also be used to support hydrogen production for use cases outside the power sector, namely industry or heavy-duty transport, and those kind of sector coupling basically creates improved asset utilization of these hydrogen storage assets, namely the electrolyzer and the hydrogen storage components. So that kind of integration we see could promote the adoption of hydrogen as a flexible electric demand resource to support grid decarbonization, but not in the sort of the conventional notion of a long duration electric storage system, where you just have electricity being the main input and electricity being the main output from these hydrogen storage systems. So with that, I will now turn it over to my colleague Rob Stoner, who will talk about the role for storage in international markets.
Thank you, Derek. Developing countries are a very important part of this story. They're already large emitters collectively, and over time will become even more important. And so implementing very high volumes of VREs on these systems along with storage is very, very important. We looked at India as a representative example, but by no means a unique example of an emerging and developing economy that is sort of characteristic of the set. India is very well supplied with electricity and has a lot of underused generation capacity. That's important to the way storage gets used there. Other developing countries, for example, many of the countries of Africa, are undersupplied. And of course, you can't create energy using storage, and so that's a very important aspect of their energy systems as well. But coming back to India, a lot of that generation capacity comes in the form of coal generation, which means they have very high emissions as a starting point. India also has very low natural gas supplies domestically. It has to import natural gas, which makes it expensive. It also has correspondingly little natural gas infrastructure for distributing gas to power plants across the country. On the plus side, it also has very low cost labor and correspondingly lower cost VRE and storage costs than we see in this country. That makes them easier to deploy economically. Critically, India, along with other emerging and developing market economies, has a higher rate of growth than we have. In India, we estimate that over the study period through 2050, the rate of demand for electricity will grow at a compounding rate of roughly 5%. That's a big number, and it means they'll be deploying a lot of new resources over time. There's also high growth as people become wealthier in these countries and they become hotter in applications such as air conditioning. A big load and a peaky load that changes the shape and nature of electricity demand through the day and year. India has excellent variable renewable resources, particularly wind and solar, which also helps to make them deployable economically. But coupled to that is a substantial seasonal variation, and so a need for storage on several timescales and backup that has to come from currently natural gas. So that had various impacts on our modeling approach. And we paid particular attention to the low-cost trajectory that was available to us from storage based on roughly the NREL projections through 2050. We also assumed low-cost wind and solar based on currently available project costs and expensive gas. And I think our expensive gas assumption, given what's going on in Europe, is probably even better justified than it was 6 months ago. So what did we see? Well, the left-hand picture here, labeled reference, shows what happens under the nominal set of cost assumptions that were made in other parts of the study. And you can see that through 2050, the high bar on that left-hand figure, we add a lot of solar and wind, and in brown, lithium-ion storage, which is our proxy for storage in this part of the study. But there's also an increase in new coal, the pink bar. If you go to the low-cost trajectory that we think is more relevant, that pink bar disappears. No more new coal gets built. And a certain amount of old coal gets forced out of the system. But it tends to linger because this is fully depreciated assets that are just sitting there running away on the grid. So getting rid of that low coal is still a policy issue that has to be taken on by the government. But there's a much larger growth in storage and as well as VREs. If you look at the bottom panels, what that indicates is that looking at 2050, for both cases, there's a nearly 50% decrease on a much larger power system in the total CO2 emissions in the low-cost scenario. This is an optimistic story, and it's not an incredible story. We think that this is very plausible. We looked at a couple of other things that we thought were important in India. One is air conditioner efficiency, which is typically low with the current fleet. If India adopts more efficient air conditioning, certainly the volume of electricity that's consumed goes down, but the load also becomes flatter, and that favors coal generation because it's better suited to flat baseline sort of demand. That tends to encourage either more coal going onto the system or certainly the retention of the existing coal. And to get rid of it as more efficient air conditioning policies are adopted, the Indian government have to be very careful about ensuring that it is either costed or through some other policy measure forced out. We also looked at urban distribution as another opportunity for battery storage. Batteries can be deployed within distribution systems to flatten peak demand at times of the day, for example, when all of the air conditioners come on. Power is delivered not through wires and upgraded transformers, but from local battery storage. That also flattens demand and favors coal generation. What we determined was that that's a very small effect on the grid. Again, an optimistic story. It's a even more optimistic story from the cost perspective and contributes to something like, we think, a 10% reduction in consumer cost, just from deploying batteries instead of wire and transformer upgrades. The study also looks, as I said, at undersupplied countries as well, and in particular we looked at Abuja in Nigeria. To make a long story short, on an undersupplied system, you can't create energy with storage. And in Nigeria, because the generation fleet is so inadequate to the task, and there's so much diesel generation offline used to make up that deficit, in a rather chaotic deployment of on-grid generation, the role for storage combined with off-grid VREs is relatively modest. And that diesel tends to linger. Overall, we think that the emerging market and developing country market for storage will be extremely large by the middle of the century. So let me summarize the key findings from that section as well as from what Derek had to say. First of all, it should be clear that I think unlike in our past studies, the situation here is very complicated. It's been complicated in our past studies as well, but it's very complicated for storage. The appropriate mix for storage, as well as VREs on a national grid or regional grid, depends very much on the available resources, the existing stock of generation and transmission and distribution infrastructure, the nature of demand, renewable resources, and so on. To get it right, modeling is key, and we think that the DOE has a critical role to play in building up its modeling capacities and work alongside the TSOs and RTOs to get the plan right in order to deliver a low-cost, reliable VRE-dominant system. We also think, and it's implicit in everything I have said, certainly in what Darek said, the role of transmission is critical. It is assumed to grow in my story. If it doesn't, the things I've said aren't true. And so transmission is critical. Again, DOE has a critical role to play in this country in ensuring that transmission projects get built in a timely manner where they need to be in order to facilitate large transfers of renewable power from one part of the country to another. And just returning to the overall modeling story then, we also suggest that it's very important to include demand response, something we haven't talked about very much here, in the modeling effort, and really understand what the opportunity for demand response within the overall system is, because that is a direct trail of investment that would have to take place otherwise in storage. In coal-dependent developing in emerging market economies, we think that storage has a very important role to play, and critically, that lithium-ion technology is up to the task today, and that governments in these countries should move forward aggressively and confidently to deploy VREs using lithium-ion, at least in the initial phase, and then deploying other technologies as they become more affordable and more available through the course of the century. So let me then turn over to Dick and the next message.
Thank you, Rob. The key word here is, in this slide, decarbonization, because the whole objective of decarbonizing electric power systems is to play an essential role in decarbonizing the whole economy. If you look at anybody's strategy for decarbonizing the whole economy, it involves getting the carbon out of the electric power system and electrifying things. So when we look at electric power decarbonization, we want to ask, well, what are the implications for the whole economy? So what we've done is to look at characteristics of efficient, cost-minimizing, decarbonized electric power system. The first feature that struck us when we looked at the results of optimizing decarbonized electric power system was price volatility. So in the graph on the right, you see in price bands the Texas system, ERCOT, from 2018 and 2019. Almost all spot prices are between $5 and $50 a megawatt hour. The graphs to the right show a model of Texas with increasingly tighter carbon constraints in 2050. NL is no limit, and then 50, 10, 5, and 1 gram per kilowatt hour. And what you will notice is that as the constraint tightens, the incidence of very low prices, $0 to $5 a megawatt hour, go up. Now, those systems are becoming more expensive as the constraint tightens. So how come we're getting more low prices? Well, think about a system without storage and just wind and solar. What do you have? You have sometimes when you have too much generation, in which case the spot price is $0. You have sometimes in which you have too little generation, in which you have blackouts or a high price to clear the market. Storage mitigates that and smooths things, but storage is a substitute for generation. Think about, how do you handle cloudy days in a system that is solar dominated? You can either put on a lot of storage, so you can take electricity from sunny days and move it to cloudy days, so to speak, or you can put in more generation so that you have enough on cloudy days. And that's substitution at the margin. And as you move toward tighter constraints, it is optimal to put on more zero marginal cost generation. So you have this combination of more really low prices efficiently and a lot more high prices. Kind of hard to see in these graphs, but you have more high prices. That's a big change. Compare ERCOT, everything's between 5 and 50, and these solar wind dominated systems in 2050, where there's a lot below 5, and you can't see it here, but a lot above 500. The other feature, and you can start to see it already, today's power systems are dominated on the generation side. First of all, there's essentially no storage in today's systems, but they're dominated on the generation side by big hulking power plants. Well, we now have a lot of rooftop solar in various places, and there's enough of it to affect wholesale markets. So small-scale generation and small-scale storage can have and will increasingly have impacts on wholesale markets. Now, we argue that reforms are necessary both at the wholesale level and at the retail level to enable these systems to function effectively and to have the proper impact on the rest of the economy. At the wholesale level, the problem is this increased volatility of spot prices. Texas, to an increasingly bad first approximation, operates an energy-only market. That is to say, generators are expected to earn all their revenues from sales of electricity, not side payments. That's going to be less attractive. It's not that attractive around the world. It's going to become less attractive as those prices become more variable. So you're going to have capacity markets. You're going to have other institutions to shield generators from those high risks. Capacity markets are difficult, they change, and none of them value storage properly. In fact, we don't know how to value storage properly. What's the capacity of a battery to help carry load in times of stress? Well, that capacity varies depending on the battery's state of charge. That'll vary from minute to minute. How do you value that in a market that says we want to make sure we have adequate capacity? The second issue, and this is a little less opaque, is you can't pay for capacity on a kilowatt hour basis or you will distort what you use. You will distort capacity dispatch decisions for generation and for storage. And of course, you can't do net metering at scale. I mean, if you want solar generation at the rooftop at small scale to play a constructive role at the bulk power wholesale level, at some point they have to see bulk power prices. The notion that you're going to pay an enormous amount for rooftop generation at a time when the system is trying frantically to shed too much generation, that's bad now. It's going to be intolerable in the future. Retail. We now have predominantly, except for very large customers, retail rates that don't vary with wholesale market conditions. And economists have been whining about this for decades. And, with all due respect to my profession, this has been kind of a small deal because wholesale prices don't normally vary that much. You saw the Texas prices, they're mostly between 5 and 50. Well, that's not going to be the state of play tomorrow. The cost of saying everybody pays the same price at all times, regardless of what's going on in the wholesale market, is going to be madness. A story everybody at MIT has heard for many times. I will tell it again. My son in Hawaii has an electric vehicle. He spends 20 cents a kilowatt hour to charge that electric vehicle, even when the Hawaiian system is frantically trying to curtail too much solar. That does not encourage EVs. That does not encourage electrification. That does not encourage customer response to changes in system conditions. So clearly, you want to encourage when the rates are low, and they will be low at the margin, the costs will be low, you want consumers to see that. Not just my son, but people who are making HVAC decisions, other decisions as to when to demand electricity, to move that demand when essentially it's free. And there will be times when it's essentially free. On the other hand, there will be times when the system is short. And there have to be incentives in place to cut demand when the system is short. We don't have the answers to this. The issue is how do you insulate consumers from excessive risks while providing adequate incentives to drive electrification when electricity is cheap, and to reduce load when electricity is expensive without imposing huge risks. As the slide says, we're going to need insurance schemes, load management contracts through aggregators. We have some of those now. We're going to have more of them. A lot more work needs to be done. So the study is pretty good at posing questions. We don't claim to have all the answers, but these are really important questions going forward. Thank you. And now we go back to the main messages. Bob, do you take the stage?
So this brings us to the end of the formal talk. I want to reiterate our three main messages here. First, that federal R&D policy should focus on long-duration storage to support affordable, reliable future electricity systems. Secondly, as you've seen, storage can make regionally tailored net zero electricity systems affordable. We've seen examples of those in different parts of the country and the world. And then lastly, that market designs and regulatory policies are need to be reformed in order to enable equitable and efficient decarbonization. So what I'd like to do now is to move into a question and answer period. I'd like to thank our presenters and then ask Howard and Kathy and Seiji to come up on stage. So we're happy to have with us some more members of the team on this study. We had about 25 of us altogether working on this study for the last 3 or 4 years. Howard Grunspecht, on your left, was executive director of the study, so he knows it all here. Kathy Wang was a graduate student during much of the study in technology and policy. She's now at NLX. And then Seiji Ingelkheimer is a graduate student in mechanical engineering working on thermal storage. So thank you all, and I open it up for questions. Yes, we have 2 mics in the aisles.
I'm Bob Hershey. I'm an independent consultant. Which of the new technologies that are in R&D look promising for solving some of these problems?
Yeah, so I've specifically focused on thermal energy storage technologies. So as Yet mentioned, there are some near-term options, reusing existing coal plants that otherwise might become stranded. But over time, as you're looking to improve performance, reduce cost, increase efficiency, there's still R&D work needed. And some of that's ongoing, and you'll see some systems maybe come online in the next decade, but there's other technologies that are further out, but could still play a role in this 2050 timeframe.
Hi, I'm Rodney Sobin with the National Association of State Energy Officials, NASIO, and just want to ask, except for towards the end, Dr. Schmalensee, there was not much discussion of distributed resources, and in the earlier portion where you were comparing the different battery and other storage technologies, there was some degree of scale there, temporal at least. Was there any discussion in the report, or can you address some of the distributed aspects? Certainly on residential, it's lithium-ion, but one can imagine at campus level, other chemistries, other systems. Can you speak to that? And also there's a resilience value not only to the bulk system, but to a given facility and to a neighborhood and that sort of thing. And then that goes back to Dr. Schmalensee's points about rate design, and I should mention that at NASIO we collaborate with NARUC on a grid interactive efficient buildings working group, so we're very much involved in these sorts of policy and regulatory issues and how to incentivize or get rid of disincentives to distributed resources, including storage, but also demand flexibility and so forth. Thank you.
Look down to the end, Paul or Dick?
There's the question. Go ahead.
Hi, thank you. I'm not exactly sure what the question is, but I think the point that Dick was making and that I would make is that up until now, we'd provided fairly generous incentives for rooftop PV and for rooftop storage. In the longer run, as those applications grow, they really need to be linked together with the bulk power system. You really don't want to have the bulk power system charging while the rooftop PV is, the storage associated with that is discharging. From a reliability perspective, it's also important that the independent system operators see what's going on, see in the technical sense what's going on. And I think in the longer run, ideally, you'd like to see contracts between load-serving entities, the wholesale market, and the owners of the rooftop and community PV and storage that basically allow them to be dispatched economically and compensate them appropriately for their being used more efficiently. There are a few areas of the country now where there now is a tremendous amount of rooftop PV and a growing amount of associated storage, California in particular. And even New England has a surprising amount, in my view, rooftop PV, since the sun goes down at 4:15 in the winter, and the system peaks at about 7 in the winter. But that's because we provided a lot of incentives to get this going, and I think we're going to have to think about it differently and find a way of integrating these two systems together.
I would just add that we've talked in terms of market issues. The same problems arise in the parts of the country that are where the utilities are vertically integrated. As I mentioned, I have a son who lives in Hawaii, and the Hawaiians have this problem in spades. They have, the last time I looked, a third of the homes in Hawaii had rooftop solar. It's not, by and large, not dispatchable, not visible, and very little stands in the way of all the rooftops in Hawaii having highly subsidized solar generation, the most expensive form of solar generation. And a lot of those homes have batteries, and nobody knows the state of charge of those batteries. That raises, we're not engineers, Paul and I aren't engineers, but that plainly raises stability issues and economic dispatch issues. So we don't have solutions to this, but it really needs to be addressed. It's not to say we want to discourage distributed generation and storage, but we don't want to treat it as a small thing that we can subsidize because it makes us feel good. It gets to be an important component of the system, integrated or not, that has to be treated as such.
I just wanted to follow up with, there are some parts of the country where there are so-called virtual power plants being operated, where residential batteries are being tapped, so there is, with those utilities, some modest visibility into the DERs, but for a lot of them, they don't know what the heck's out there,
Right.
which is a lot of the problem.
Central
But I did want to get back maybe to the technology about, lithium ion is sort of the winner in the residential, but for more industrial or campus, maybe some of the other technologies may be useful, and I have a fear of lithium ion, there being sort of the technology sort of gets embedded, and then we miss some other opportunities with the other, the Betamax VHS question, it's inferior technology.
Well, I think you.
Well, I don't think we're there. I don't think we're there. I mean, it's embedded in the sense that the cost of lithium-ion batteries has gone down rather dramatically, and there's obviously a use case in electric vehicles, but also on the grid. If you look at this country and European countries, right now anyway, the need is for short duration storage, less than 4 hours in England, maybe 4 hours here, so that there's time and opportunity to do the R&D to create other options going forward where longer duration storage would be potentially more economical than building one lithium-ion battery after another to get a longer duration.
It's important to recognize that we don't see the kind of network effects here that were present in the video recorder world that drove there to be a single standard. I think we all anticipate a future in which there are multiple storage technologies playing multiple roles, and there's no reason why one would drive out another other than sheer cost dominance.
Especially
And if you want one, I have a
storage is
Betamax in my attic along with an Apple II.
Okay, yeah.
Yeah, we do spend some time in the report on attributes of these technologies that make them scalable down. And so, for example, the thermal storage that Seiji talked about, that's not going to be scaled down, right? But lithium-ion is particularly well-suited for scaling down, obviously. Some of these other technologies differ in their ability to be scaled down, for instance, residential scale. And I think some of the lowest cost ones are better scaled up, and that's why they're likely to see deployment at that larger scale.
Yes.
Hi, Karen Marcy, US EPA. I think that in today's markets, we see that like short duration battery storage is, the revenues for those technologies is primarily driven by ancillary and capacity markets. And like intuitively, longer duration battery storage would get its revenue from like the energy markets and the disparity of prices. But in your future deep decarbonization scenarios, you're showing lower marginal prices. So I'm wondering, in the modeling that you're doing, are you seeing, what is the primary revenue source for these technologies? Is it energy, or is it the capacity in those, that 4% of the year that it's greater than?
Yeah, so in our modeling of the bulk power system, we focus primarily on the arbitrage function that storage plays a role. In some of our other work, we have investigated sort of the revenues you could get from ancillary services. But as we have seen with PJM and some other regions, that market quickly gets saturated and is relatively small compared to the, the market for energy services. So, that's been our primary focus. We didn't model any capacity remuneration schemes in that system. So, the assets have to make up all of their revenue, then break even primarily on energy generation and arbitrage opportunities.
And I think you have to look at this dynamically. Right now, there aren't the arbitrage opportunities in most parts of the U.S. and Europe because the penetration of wind and solar is still fairly modest compared to our analysis for 2050. As Derek indicated, selling regulation, frequency regulation, there just isn't that much of it. You crush the market very, very quickly. So the arbitrage opportunities will increase over time as the penetrations increase. And for example, you can see it in California where there is a consistent gap between the midday price at noon and the 6 or 7 o'clock price. It varies from day to day and the level varies, but you can see there's an opportunity to buy low and sell high, and that's what's going to happen in more and more places as penetrations of VRE generation increase.
I would just add that storage is hard. Derek and I spent, weeks looking for rules like the standard economic dispatch rules that govern generation. And one of our graduate students took a look at how storage actually behaves in our optimizations. And, sometimes long-duration storage makes short cycles. If that's what's wanted, it'll discharge for an hour and then charge up again. And sometimes lithium-ion will run the full 4 hours. So exactly what the revenue opportunities will look like will vary from day to day and from market design to market design. Storage, we have come to understand, is more complicated than generation when you look at a system.
Kathy, do you want to comment on that, or no? Okay. All right, we had a question over here on the left.
Sure. Yes, Dan Shaw of Resources for the Future. Thank you all very much for doing this study. Do you have any advice on government support for research, development, and demonstration of long-duration storage technologies?
Want to start, yeah?
For sure. Yeah, you've seen a number of initiatives that have come out recently from the government on long-duration storage, and I think those are headed in the right direction and spot on. One of the things that these long-duration storage technologies don't have is another market that helps propel them. We commented on how the growth of lithium-ion for EVs is actually, a competitor for grid storage. But on the other hand, the benefit has been 3 decades of lithium-ion has really, dragged along the technology. Now we can consider it for grid as well. Right? Some of these other technologies don't benefit from that. Right? And so they in general, we think, need more support. They're also not as mature, and what you see in the marketplace is that, for example, in EV batteries, the amount of private investment has gone up tremendously over the last decade, and it's probably appropriate for the government to taper back on support of that R&D. Right? And so this, what we're recommending, and independently what we see from the coming from the government in this focus on long-duration storage, I think is in sync.
I'll mention that in the technology area, technologies that can benefit from other sector opportunities, we've mentioned hydrogen as one of those. A second one is thermal. There are a lot of places in the economy where having thermal energy is very important. Process heat for industry, perhaps from hydrogen, but maybe from other sources. Heat for space conditioning in buildings. Another example. So it's possible to look at some opportunities for thermal coupled with other parts of the economy that could be very useful in driving those costs down. The other thing I'll say is that in addition to the deployment opportunities, which I think we're at the early stage of because we still are fairly low penetrations of solar and wind, we need to keep the pipeline full of new ideas. Ideas for metal iron batteries, for example, are pretty young in the perspective of other storage technologies. And I think we need to keep looking for technologies like that might be out there in 2050 to help us get to the goal.
So just another thought that I could add is that on the demand side, for instance, even the utilization of pumped storage hydro, which we have, but the move toward natural gas generation, which is on the margin both in the day and in the night in many places in the country, kind of remove some of the utilization rates of pumped storage hydro, which is our current long-term storage option, have actually tended to fall off as gas generation has become a larger share of the overall. So, for instance, when we were building large nuclear and coal plants in the 70s, and oil was the fuel for peakers, the tremendous cost difference there really motivated the notion of, gee, I'm going to run our nuclear plant, our coal plant, 24/7, and then at night we'll use the excess energy to pump water up so we don't have to run oil peakers, during the day. Well, that kind of goes away. So there's a demand side issue as well as a supply side issue. And as many have said, as we get more and more into the wind and solar, maybe we'll start to see the demand side pick up as well.
So just adding to Bob's point about hydrogen, I think the recent initiatives around the clean, the hydrogen Earthshot and the goal of $1 per kg by the end of the decade, and the effort around hubs for hydrogen, they don't directly sort of address storage, but I think in the way we've looked at some of our modeling and how hydrogen can interact with the electricity system, reducing the cost of producing hydrogen from electricity will certainly make it attractive for use in industry or other applications that then also has an implication on the grid as being a very, potentially a flexible demand resource. And so proving out those technologies at scale will also, implicitly support the ability to integrate larger shares of renewables on the grid and provide that longer-term demand flexibility that we don't have on the system today.
I just add the following comments. There's no simple definition of long-term storage. It's you know, it's endogenous. It's a system outcome. It's storage that is economical or potentially economical to be used in an efficient system if it's proved out, and it's going to be more economical than just continuing to add modules to lithium-ion batteries. And the danger is, from my perspective, is there are people out there with the ideas for long-term storage where they think long-term is 4 months. And they're really, we can't see an economic, or I can't see an economic case for that, but I could see someone coming to the DOE or someplace else and trying to make that case, and you'd end up flushing money down the toilet. So I think, you know, we go back to basic principles. Are there learning opportunities? Are there basic science opportunities? If this pans out and you put it in one of these models, is it chosen for a least cost system? Because I think there do have to be, you do want to have some constraints on where you put the government's R&D money, and it shouldn't just go to the wildest ideas that are just never going to be economical.
So I'll add an example. Early on in this study, we heard a presentation from a very distinguished UK academic addressing the question of how much seasonal storage did the UK need, because offshore wind, I think, blew more in the winter than in the summer, and how much did you need to carry that excess from the winter to the summer? And on a quick look, the answer was none. Just build more windmills, for heaven's sakes. But if you start out with the notion that, no, we're gonna carry it for 6 months, you end up with a lot of storage.
One observation, over time, the definition of long-duration storage has changed. It's become longer. So I've been in the battery game long enough to remember when long-duration storage meant 2 to 4 hours. And so I think a more precise definition today would be multi-day. Right? Although there are places where, you know, those 4 months might come in handy, such as Antarctica. Right? You have a half a year of sun and a half a year without. Right? But that's not, obviously not our main focus.
Cyril.
Cyril Draffman, U.S. Nuclear Industry Council. Also, I thought it was interesting about talking about the materials availability. I'd be interested in driving forces around the world. Where do you think the development for energy storage, particularly long-term, is going to occur in the world? We talked about China. And where might it be deployed? I mean, Rob touched upon Africa. But is there, because of the capacity markets, the way they're described in other parts of the world, I'm interested in where are the driving forces around the world, either for the development side and for the deployment?
Sure. So I think Rob spoke to the role of the developing market, and where there is, electricity generation capacity, that's where storage can serve a role. I think on the one point that I was going to make on the previous discussion is we talk about scalable a lot, and that was this theme of kind of manufacturing scaling that went throughout the report that we haven't really talked about so much today. But I think that where we have opportunity, particularly in the US, to start to think about what the manufacturing capability should look like in order to help with deployment, because we've made a case over the course of the past hour today of the fact that there could be driving demand here locally, but not in any way in the development manufacturing capability of that. And even if we look at something like battery recycling, lithium-ion battery recycling, because of the lifetime of the battery pack, the current post-consumer volume is very low, but there's a wave coming. But most of the capacity, manufacturing capability to manage that end of life, storm that's coming has been in Asia and continues to be, such that even the manufacturing scrap that comes out of any plants in the U.S. is going to China. And so I think starting to anticipate that a little bit when we think about what the manufacturing opportunity is and what the deployment is, given the fact that there is, we've heard over the course of the day-to-day a couple of the scenarios where we think that there will be driving interest here. And I think Rob spoke to the sort of international role of places like India versus Africa.
Yeah.
Maybe to give a U.S. case study on that scalability question. So one of the technologies I've been working on is iron air batteries. And if you look at the, let's say the U.S. Deployment in mid-century, 5 to 10 terawatt hours. Right? you would need about 10 new iron production plants at the average size that's in the US today. Not a huge lift to get to that. And it would cost you about $10 billion per terawatt hour of deployed storage. Right? And that could happen with entirely US iron. Right? So that's an example where we don't have to rely on supply chain that is in other countries. And the scaling could probably take place in the time that you need. Right? So that's attractive, and that's something that I feel personally pretty bullish about. Right? So there are such options, and and the thermal storage option also. Obviously we don't need a overseas supply chain to build thermal storage media. Right?
We have plenty of rocks here.
Well, you need an old power plant.
We have those too.
I mean, I think there's a strong regional bias to manufacture within market because of the relative bulkiness of batteries, especially a lot of the long-term duration storage technologies that we've talked about. Iron is produced in abundance in India, for example, and it would be absurd to import iron batteries from China.
Right.
I think there's also a recognition on the part of many manufacturers of lithium-ion batteries, Chinese manufacturers, but not only, that they're at some risk if they manufacture domestically and try to export, that those exports will be subject to tariffs in a way that they haven't been in the past. And we see that happening in the United States.
And even for grid storage, even the prevailing lithium ion is likely to become iron-based, lithium iron phosphate. And we're already moving quickly away from both cobalt and nickel. The lithium is still there. Right? We addressed that earlier. But lithium iron phosphate is, again, iron. So just remind everyone that the Earth is basically a big ball of iron. Right? So every continent has iron.
And air.
And air.
It's probably worth then coming back to the system studies, which showed the richness of the differences in how you'll deploy storage and what kinds of storage you might deploy in different parts of the U.S. or different parts of the world. Any other questions?
I was going to add, you're going to use hydrogen to reduce the iron, right?
That's right.
That's the other connection.
That is a front runner in the decarbonization of iron and steel. Yeah. Any other questions? Yes.
Would any of you like to talk about more about the role of major uncertainties in the future of long-duration storage? What you think perhaps some of the biggest uncertainties are, and any advice you have on dealing with those uncertainties in policy making or in research?
So, from the systems integration piece, I think, a lot of our analysis kind of suggests that, storage competes with a lot of other resources, right? So the market for long duration storage is determined as much by their own costs, but also by the cost of the other competing resources, right? So if you think we are not able to, quote unquote, overbuild renewables to sort of tide over some of these low generation periods because of other factors, whether it's cost, whether it's, land availability, siting considerations, then long duration storage could look much more attractive from a cost proposition. That also applies with transmission expansion. So there's some significant, interdependencies in terms of the trajectory for these technologies that we largely overlooked, and we try to sort of look at it on a scenario-based approach. But the underlying drivers become clear when you sort of compare those scenarios and see that the market could be very big, could be very small. It really depends on, how some of these other factors play out that are independent of just the technology, cost and performance attribute.
I think the story in the simulations that Darek showed between 5 or 1 grams of CO2 per kilowatt hour and 0 are very revealing. Things get really, really hard when you go to 0 in the system. I think in that limit, as we get down to very deep decarbonization, that there's also, I think, risk to the long duration storage technologies, or maybe a complement would be a better way to put it. with zero emissions generation technologies, so flexible generation technologies. And we are working on those. We, in the US and globally, are working on those kinds of problems. I think fusion is very interesting technology. Looks more promising than it did 10, 15 years ago, but there's still much to be done there. Geothermal has some interesting new approaches to very deep drilling to access geothermal. Interesting new CO2 power cycles on the back end of thermal generators, the so-called Allen cycle. Interesting ideas around burning biomass to make electricity, but capturing the CO2 off that to get a negative emissions technology. So I think there's a lot of interesting complementary technologies out there that will have an effect on what we do in long duration. But again, and again, I think those impacts will be different in different parts of the country and world.
I also think there are huge policy uncertainties. Just to give you one example, our model kept wanting to build onshore wind in New England and New York because it's so much cheaper than offshore wind. And talking to people, the answer is you simply cannot site it. It may be cheaper, you can't site it. We have studied the impact of transmission. Transmission, particularly transcontinental transmission, has a lot to be said for it in terms of cost and impact. Will we be able to build it? Our model calls for expansion of transmission in various regions. Will we be able to build it? I tried to pose some of the regulatory problems involving market design and retail rate structures to get the economy to efficiently decarbonize. Will we be able to do it? I have no idea.
Other comments? Okay. Yes, another question?
Yes, feel free to tell me that three is too many, but if you'd like another question,
I'll tell you after you ask the question.
Okay. So again, Dan Shaw, Resources for the Future. Up to what duration did you find would likely be, say, profitable on-grid in the U.S.? You mentioned earlier the example that someone had come and talked about the value of storage with a 6-month duration or something like that because of the mismatch between offshore wind resource and consumption, seasonal highest consumption in the UK. But in fact, you don't need a 6-month duration to accommodate that. In reality, up to what kind of duration, that is, up to what kind of ratio of energy to capacity did you find indications that would be worthwhile on the grid in the US?
Yep. So in most of our cases, we do, when you do look at scenarios with significant quantities of long duration energy storage, we're sort of building, on the order of, again, as Yet mentioned, multi-day storage. So we're talking 40 to 50 hours. I think one caveat I'll mention there is that for some of these storage technologies, that duration is defined typically in terms of discharge power capacity, the ratio of energy capacity to discharge power capacity. But for some of these technologies, you can also independently size your charging capacity. So your duration of charging could be much longer, where, say in the case of thermal storage, you're trickle charging over a much longer period of time, and then your duration of discharging could be much shorter. So I think the definition of duration, you have to be careful about how you define that. But generally speaking, in the conventional notion of how duration is defined, we see sort of on that order of multi-day storage in the scenarios where it does get deployed, and that tends to be sort of in the 0 gram per scenarios that we looked at. Yeah.
Right, and I think another related factor is that in our modeling, I think we did look at, and Derek is obviously the expert on this, but on the supply side, we looked at the impact of changes in wind and solar over multiple years of data and incorporated that in the analysis. On the demand side, though, we did look at increased electrification, but only based on a particular sort of target year and target weather. And the real question is, as we move to electrification of, let's say, home heating, which is a huge, consumer of fossil energy, natural gas, propane, oil. The question is, what if there's sort of a correspondence between demand, unusually cold weather, let's say, not the weather in a given year, but preparing the system for a demand peak that might coincide with a supply trough. And then you make, and I really think in almost all the studies that have been done, I don't think the variability of demand in an future electrified economy, has been looked at. That's not unique to our study. I think our study was done pretty carefully, but it does have that limitation. So again, it might look very different if one had to prepare for the if you had the polar vortex, which might not have been in our base year, and polar vortex in a electrified heating world on top of everything could change the amount of long duration storage.
I will mention we have one, in almost all of our runs, we have one form of long duration storage that's not labeled storage. We allow the system, as part of its optimization, to build natural gas plants with carbon capture and sequestration. And unless you go all the way to zero, since carbon capture isn't 100%, it does build such plants. It doesn't run them much. It runs them with very low capacity factors, and it runs them optimally when, oh my God, the wind doesn't blow for 3 weeks. So you run the natural gas plant. Well, that's long duration storage in a way. It's replacing long duration storage, but it begs the question of how exactly are you paying for the infrastructure to let those gas plants run with 2% and 5% capacity factors. Extraordinarily valuable to have them there as a substitute for weeks of storage, but expensive if they have to carry the full pipeline cost.
One more point on the duration. The input for the model is the cost of the batteries or other storage systems. So we went back and forth for a very long time trying to converge on what cost numbers to use in the modeling. And so the results are based on the input. And the simple fact about storage is the cheaper it is, the more of it you'll use. And so the duration is also sensitive to cost.
And then it becomes more subject to the materials availability costs and the volatility of that. And we've looked at the sort of implications on price of materials over time in high demand, low productivity on the mining side perspective. So there's a play that becomes the supply chain's even more critical as we're driving those costs down.
And I'd just like to emphasize a point that Howard made. It's not just the increased variability in demand, because we'll have more weather-sensitive demand, but it's the correlation both between demand and supply, which we normally don't think there's necessarily a correlation, but also a high correlation between generators. So today, if in the summer, you may have forced outages for, a few hundred megawatts of gas plants in August, but when the wind doesn't blow, they're all out. Or at very low production. And that's not something we typically see today. And unfortunately, we saw an example of this, not in the context of wind and solar, but in Texas in February, when so many gas plants went out at the same time because of the very frigid weather. And in that case, the outages were highly correlated, obviously. And that could become more of an issue in especially a wind-dominated system, perhaps a solar-dominated system. And these two dimensions of correlation really need to get built into our modeling and into the planning and market design process, because they're quite different from the attributes we see today in thermal systems.
So I want to thank you all. I think this has been a very interesting conversation. I think it's helped us to bring out the points in this study that we have to have a deeply decarbonized electricity system to help decarbonize other parts of the economy. That's going to require storage, long duration and short duration storage. We need technologies for that long duration storage to enable us to get to these highly decarbonized systems. We need systems planning tools that allow us to design, operate, regulate those systems of the future. And we need improvements in the market structure design, in the policies and regulatory scenarios So these are all things we need to get to the future, and I think it looks bright. I think we see ways to get there, and I again thank the panel and the discussants for this, and for you for being here. Thank you.